Hello calculus folks, this is Mr. McAllen again, and today we're going to work on a Taylor polynomial and estimating error when our interval for which we're going to use the approximation will only be used between negative 0.0, negative 0.1 and 0.1. So what that means is we want to see what our error will be if we're going to just stick within this interval for approximating this function. So here we go. First of all, we have to look and remember that our function, which is the square root of 1 plus x, is being approximated by a polynomial of order n plus the remainder, the nth remainder term. So we're going to, and if the remainder term is 0, then the polynomial would equal the function. But in this case, because we're only using 3 terms to represent this function, we're going to have some error associated with it. So now what we want to do is estimate our error by using the remainder theorem. What we do is we consider, since we're using a polynomial of order 2, and the order comes from, or degree comes from, what our power is, we're going to then use a remainder of degree 2. So what we do for a remainder of degree 2 is the remainder of degree 2 is just the next derivative at some value c that maximizes our third derivative multiplied by x to the third power over 3 factorial. The c value should be chosen with care within this interval, as I said before, to maximize the third derivative. We want to get a maximum bound on the error. So let's start. We want to take we know our zeroth derivative of this function is going to be just the function 1 plus x. Our first derivative is going to be 1/2 of 1 plus x to the negative 1/2. Our second derivative will be 1/4, negative 1/4, 1 plus x to the negative 3/2. And our third derivative, the one we're interested in, will be 3 over 8, 1 plus x to the negative 5/2 power. I'm going to take my remainder term, and I'm going to consider that to be the maximum error. Okay, and when I consider error, I'm going to consider absolute value of error, because error is error. It doesn't matter if it's above or below the value. So when I rewrite this, I'm going to say my error is going to be less than the third derivative. So I'm just going to put in the third derivative, 3 over 8, 1 plus x to the negative 5/2, and I'm going to put x cubed, and that's all going to be over 3 factorial. Now it's important that this x value that I choose, or that I'm going to choose, is going to maximize this term right here, which is the third derivative term. So let's rewrite it in the form that will make it easier for us to see that. I'm going to have 3 over 8, and the bottom is going to have a 6 from the 3 factorial. I'm going to put the 1 plus x underneath the square root, and then I'm going to raise that to the 5th power. Remember, power over root. And since I moved it to the bottom, that power became positive. And I'm going to have x to the 3rd power in the numerator. Now, I'm trying to maximize this derivative term, so I would like to make the denominator as small as possible. So if I have a value to choose from between negative 0.1 through 0.1, if I choose the left endpoint of negative 0.1, I'll get a smaller value than I would if I chose 0.1. Because if the denominator becomes bigger, the error term becomes less, because it's in the denominator. So what I'm going to choose from my maximization terms, I'm going to choose the value of negative 1. And now I'm going to rewrite this. I have 3 over, this is 48. In the radical, I'm going to have 0.9, then to the fifth power, and in the top, I'm going to have 0.9 to the third power. When I calculate this on my calculator, I'm going to find, let me pause it, and then I'll put the value up. Okay, I beg your pardon, but I made a correction here because before I had 0.9, and that was really where the x value went. So when I put in the correct value for 0.1 and I work out all the math, I've got an error that will be less than or equal to 8.13 times 10 to the negative fifth power. So what that basically says is any value that I choose inside this interval will be no more than that error. So let's see if this holds up, and we'll graph the function on the graphing calculator, and just to prove out what the actual error is and show that the remainder estimation theorem gave us a boundary for that error. So here we have our function. It's 1 plus x under the square root, and you can see on the right that it shows a square root function moves to the left by 1. Here we have our three-termed polynomial, and you can see we have color is like kind of well, we could work with that color later, but now you see the subtraction over here of the function from its Taylor polynomial, and we'll see what its error looks like. And as you can see in this region, right here, you see that the error is pretty small. You can see with the y values basically dictate what the error would be. And since our error band, or our interval for x, is from negative 0.1 to 0.1, we can actually verify that where is our maximum error occurring. So I'll just type in 0.1, and we see that we get an error of 5 times 10 to the negative fifth. And then if I type in negative 0.1, negative 0.1, maybe the negative should come first, 0.1, we get even more error. So it shows that the error is not symmetric, and it shows that we chose the correct side of the interval to use, the one at 0.1. And the other thing, people might get worried and say, well, these numbers don't match what we had as 8.21, but that was a maximum formula. We were finding the max error that it could possibly be, and it falls within the these error values right here fall within fall underneath the maximum error. So and this is what the remainder estimation theorem is all about, is using that last term to characterize the maximum error we could have. Hopefully this video has been of help to you, and if you read below, you'll see that the next problem I'm going to be working on that I'll post up will be, what would the acceptable x interval be if you wanted to find your maximum error. So this problem that we worked on, they gave us an interval, or the problem, we were given an interval to find what our maximum error would be. Now we're going to work on a different problem, but be working backwards, where we say, if we know what the maximum error is allowed, what would our acceptable x interval be? So tune in for that video. It'll be right after this video, and then you should have a handle on how we are using the remainder theorem to solve these types of Taylor polynomial problems. Thank you for tuning in, and please, if you like this video, please like it and subscribe to this channel.